Hello and welcome back to the Code Athlete. Today we're going to have a look at Kickstart Round F 2021 and the problem Star Trappers. This was solved during the competition by 2% of all participants, but overall I think only 10% even got to this problem and tried to solve it anyway. The problem statement says, John and Ada are sitting on the grass above a small hill. It is midnight and the sky is full of stars. The sky looks like a 2D plane from so far away, and the stars look like points on that plane. Okay. Ada loves blue stars, and suddenly she notices one while all the other stars in the sky are white. Okay, so there are blue and white stars, but only one? Yeah, she loves the blue star so much that she wants to trap it. And she asks John for help. Ada will tell John the position of the blue star, and he has to trap it. John has to draw a polygon in the sky with his buster's board, so that the blue star is strictly inside the polygon, not in the border of the polygon. Okay. And the polygon has the smallest possible perimeter. So not the smallest possible area, but the smallest possible perimeter, okay. The vertices of the polygon must be the white stars. Ah, okay. I was wondering, because if there is no restriction on the construction of the polygon, why not make it as like an epsilon small polygon? But okay, we have to use the white stars. Even though John is super awesome, he needs your help. Given the positions of the white stars and the blue star, you need to find out whether John can trap the blue star. And if he can, also find the minimum length of the perimeter of the polygon he will use. Is it allowed to have inside the polygon also white stars? No, I don't think so. And I think there are cases where actually the smallest possible perimeter is can have white stars inside. So it's not better to use those white stars as vertices of the polygon. Okay, let's finish reading the task. For each test we have t-test case. Sure, for each test case, first line contains an integer n. That's the number of white stars. The next n lines each contains two integers, x and y position. After these n lines, there will be one last line which contain two integers, x and y again for the blue star. Sure, easy enough. So there's exactly one blue star every time and many n stars that are white, which we can use as vertices. And I guess we output the perimeter. Yeah. And if it's impossible, we print impossible. Sure. Y will be considered correct if it is an absolute or relative error of 10 to the minus 6. Sure. Test set limits 10, 445 and 300. For 10 test cases and 40 test cases. Oh no, sorry, it's a timer. Yeah, there are 100 test cases. The remaining 90 have only 60. So n is not super large. We can do something like n squared or n to the power 3 even, I guess, from the algorithmic point of view. Let's look at a few examples here. First test case, we have only two white stars, so we cannot draw any polygons. Okay, so I guess polygons have to have positive area. Yeah, because the blue star cannot be on the edge. Sure. Ooh, bit tired. So the second, let's just check. It's 0, 0, yeah, just 2 points. Doesn't matter. The second test case, we have three white stars. So we can draw only one polygon, a triangle, as shown in the picture below. It turns out that we are able to catch the blue star. Also it's at 1, 1. Yeah, okay. Length of the perimeter is 5 plus 5 plus 5 times square root of 2, Pythagorean equation. Sure. Does make complete sense. So let's think about the problem, and the first thing which I was thinking about is if there is a case where we enclose also white stars. I was thinking of something like this. Then I'll have blue here because blue is hard to see on black. Let's take maybe red. And now I think now actually the optimal polygon would be something like this, I guess. What I was wondering if we have to, let's say we have a different example. Let's say we have this setting here. Because now, and let's assume this blue star is, I will call it now the red star. If this red star is in between these two exactly, it would be on the edge. So I can't use this edge if I use this star. And also together with these two, I mean, I could use this polygon. This would be actually allowed. But that has a longer perimeter than taking a shortcut here using this. So I think this is the optimal solution in this case, and we would have had a white star inside. Yes. Okay, so there are these cases which we have to watch out for. Now the question is, how do we find the optimal set of points? Maybe we should first try to figure out if it's even possible or not. And I would say that given some points, we want to take the convex hull of this hull. The convex hull would be this here. Basically similar to putting a ribbon, an elastic ribbon around nails on a board. So the ribbon would go like this, not to this point here, because it's inside the convex hull. So this would be the convex hull, and if the point is outside of this convex hull, we can't create a polygon. And if it's inside the convex hull, then obviously the convex hull itself is one such polygon which would be a solution, and then we just have to find the minimum. So I guess that's an easy criteria, and maybe we can now also start our algorithm with this convex hull and reduce it. That's what I'm thinking right now. But I'm not totally sure how. One thought was to maybe triangulate this convex hull like this. Check in which triangle our red star is, and then we could shorten these outer sides already. Problem is there are many triangulation possibilities. I could also triangulate like this. And then we have the inner stars, which we have to use. Also, there's this special case. Here, if we have 4 points. So I was thinking, is it always a triangle, the optimal shape? But I think, for example, in this case, where our red star is again on the connection lines of these two and these two, we can't choose any 3 points to include this red star. So in this case, we would need to take all 4. But I guess in the case of 4 points, the red star has to be on this intersection, because if it wouldn't be on this intersection of the 2 diagonals, let me draw those 2 diagonals, this one here and this one here. If it would not be here, but let's say maybe only on one of the 2 diagonals, then we could shortcut the other diagonal, basically use this diagonal and throw away the other 2 because of the triangle inequality. This would be a smaller perimeter. So if it's a 4-star configuration, that's only optimal of the red stars in the intersection. Let's think about maybe 5-star configurations. And so with the assumption that this 5-star configuration is the optimal enclosing polygon, or the trap, how it's called in the problem statement. So you could use these 4 stars if the red star is here, or these 3 stars if the red star is up here. So we know now that the red star has to be on this diagonal in order to be this 5-star thing optimal. The same is true for this diagonal, this diagonal, this diagonal, this diagonal. So for this 5-star configuration to be optimal, basically the red star needs to be on all these intersections, or you could say this intersection basically should be the same point as this interaction, which also means that this white star would lie on the connection line between these 2. Okay, so it couldn't be like this 5-star convex polygon thing. We now know that there need to be, in that case, 3 on 1 line. Not sure, maybe the problem statement says that's even not the case. We will not have the same position again. I mean, in this case, I guess you could say if 3 are on 1 line, 2 are like this, then you could ignore this 1 point. Wouldn't make a difference, it's basically a 4-star shape. Can the resulting polygon be non-convex? Actually, that's an interesting question. So a non-convex polygon would be maybe something like this. We have here this non-convex edge. But I think in that case we can always make basically the area bigger, because we know already the red star is somewhere in here. But we can shortcut the non-convex diagonal. The definition is basically that there's a diagonal outside of the shape, and we could use that instead of the inner edge, because it makes basically, it still includes a red star, but it makes the perimeter smaller. So the polygon has to be always convex. That's helpful. And then we now basically have proven that it's never a 5-edge polygon, because this was the general. Of course, it doesn't need to be that symmetrical, but the point was, if we have 5 different points and not 2 of them lie on one line because it's convex, then basically we can always make it smaller to 4 points. Like this lies basically here, then we can ignore this, and then the red star could lie on this intersection of these two. So here. And then this 4-star configuration is optimal, and otherwise we can always go down to 3 points. So that's also good to know, I would say. Interesting problem. Now I'm really not sure how to iterate through all the... Oh, maybe if we know that it's only 3 or 4 stars, maybe we can actually really iterate through all 4-star selections and 3-star selections. Because n is not that big, remember I said that? Interesting, that might really work. How many possibilities are there to select 3 points out of n? Well, the answer is n over 3. This is a binomial coefficient, and you compute it by, basically, you have for the first point to select n possibilities, for the second point you have n minus 1, because you already selected 1 point. Then there are n minus 2, and now you have selected 3 points, but the order in which you select them doesn't really matter, so you have to correct for this by dividing basically by 6, because there are 6 possibilities to reorder 3 points. So, and this is, I mean, you can see this upper is smaller than n to the power of 3. And the size of n was like 60 in a lot of cases. So n to the power of 3 is something like 60 to the power of 3 is roughly 200k. Oops. 200k, or the other limit was, in 10 test cases we have 300. Okay, that's a bit bigger. That's 27 million, actually. But still fine, still fine. For 10 test cases, that would be fine. Now the problem is with these 4-star shapes, because now we actually have to, n over 4 is much bigger again. It's roughly to the power n to the power 4. That is okay for, what did we say, 60 here in the remaining test cases. That would be still, yeah, 12 million, just 12 million. But for the 300, I think it's too much actually. It's 8 billion. Is 8 billion too much? I always have the rule of thumb that in C++, 1 billion iterations roughly takes 1 second times the number of iterations you do, the number of computations you do inside the loop. So the computations inside this loop, basically checking one such 4-star configuration and checking, basically we need to compute the perimeter to find the smallest one, and we need to check if the red star is inside. So it's a few computations, a few multiplications as a basic unit number of floating point operations. So it would be like in the 8 billion case, it would be 8 billion times, I don't know, maybe 100. Not 100, maybe 20 floating point operations. Anyway, 8 times 20, that's like, and that's seconds. So we would have 160 seconds and our time limit is 50 seconds. So we can't do that. But we also know that in this case, when we select 4 stars, there needs to be actually an intersection. So actually it's similar to, basically if we know it's this intersection, we can always say, oh, as soon as we have 1, 2, 3 stars selected, and we know where the red star is, first of all, it needs to be on this on the 2 diagonals we want to have. So if it's basically on this edge of the triangle, we can say, oh, this here needs to be the other star on this line somewhere. Or if the red star is in this position, then the other white star needs to be on this line. Or if this red star is somewhere on this edge. So basically we have only one of these cases. We can say we can check where the red star is. If it's not even on any of these 3 lines, there can't be a 4-star configuration containing these 3 white stars. So then we don't have to check, and if it's on the edge of one of those, we can say without a loss of generality, we can say it's on this edge, and then we can check on this, taking the other point of the triangle and constructing a long beam basically, and checking if there are any white points on there. But that's still a factor of n, checking all those points if they are on the beam. Is there maybe a hash? Hash how we can do this? We could first iterate through all pairs of stars, that's n over 2, which is in the order of n squared, and that is very fast for all the numbers of n we have, and check if those 2 are basically in this configuration where the red star is in the connecting part of these 2 stars. And if we save all those pairs, then we can easily look up, was this star part of a pair? Or part of multiple pairs even, and then we can check all its other stars that it points to. And this we can actually store in a lookup table. So I guess that's fast enough and should be the solution. Yes, so we only need this n squared in the beginning and the n to the power of 3, which is small enough even for the 300 star case. So we can iterate over all. So that's surprising actually, that we can basically iterate over all multiple polygons that make somehow sense and just check which one is the smallest. So nothing really too smart except the realization that we only need triangles and in some very special cases quadrilaterals. We call them? In German we call them Vierecke, 4 corners basically. So let's go to the implementation. We have endpoints. We have the cell abbreviation data type, which is basically, I don't even know, a complex with integers. Because the coordinates are all integers, right? Yes. List of cells, stars, and the blue star. I will call it now blue again in the code. I'm not sure if this is correct. No, it doesn't seem to be correct. So cell is a complex data member. So the question I'm having is how to assign this, and I think there was not really actually a good way. I always have to do this. That is fine. Then we need our dictionary of connecting lines. So I will do this via the ID of the stars. So it's a dictionary. For every star ID we have a list of stars that is producing a connecting line where the blue star is on. Connects through blue. Let's clear this. For every new test set, but we will do the calculation inside the calc function. Yes. Oh, and actually the result is we have a default value mode, because at some cases there is no result, and yes, the result size. Okay, result is actually a float, long double, and we just check if the result is 0. So we can set the result 0. Yes. But we want the minimum, so maybe it's easier to set it to inf. What is in our case the inf? I'm just looking at the values x and y can have, so because they're in a square basically of size 10 times 6, we have 4 times this edge of the square, which should be the largest possible circumference or perimeter. It's 4 times 6. And let's say 5, so that's really bigger. And we can check this here. It's the default value trigger. So in that case we will write impossible like the program specifies. Now the connecting lines. Start point. Endpoint. We only need one. Do we want to have bidirectional? Yeah, I guess, but we only need to check one, and then the other one automatically is also. So we always will add both into the connects through blue, not just one directional. And the lookup is easier. So if line contains blue, start, end, index, and that's all we need. Then connects to blue of start as the end index and the other way around. Line contains blue start, oops, end indexes. And we need to have perfect precision here, basically. So we will stay in the integer realm and don't divide y by x to get the gradient or so, because that might be too inaccurate. We will transfer all into the coordinate system of S, basically. So we will have because if we transfer to the start point, then the start point will basically be 0. The other white point will be star E minus our origin now. And rel blue will be blue minus our start point. And now they are on a line if there's basically a factor with which I can multiply rel blue to get other white, and this factor needs to be positive and larger than 1. 1 cannot be, because then this white and this blue star would be the same, which is excluded from the problem statement, the case. Yeah, just have to check we can't divide by 0. So rel blue can't have both entries 0, because then blue would be equal to the start point. So yeah, if rel blue dot x equals 0, let's say not equal 0. In the else case, y is not equal to 0. In this case, we can say k is equal to other y dot x divided by rel blue dot x. This division is okay because we divide by non-zero. Else k is equals. We take the y component. If k smaller or equal to 1, turn false, because then the blue star is outside of the line. It might be exactly on the line, but we don't care, it's outside of the line anyway. If it's bigger than 1, we have to check that actually if we multiply, if blue times k equals to other white, so that the math is exact, because here this is a round down operation, so this might be, k might be inaccurate. X blue times k might not be exactly white. Only if that's the case, it's really on the line. So in this case we have true, otherwise we have false again. And we have to turn on the xy notation, which we use here for the complex numbers. Oh, and then we cannot use xy here. Position x, position y. Yes, so that should be fine. Actually, I will just have a look at this. Okay, now we need to go through all the 3 star configurations. And just realizing, because we need to make set looks up, so this should probably be a set, and here we need to insert. Yes. Star 1. Star 2. And here we basically have this factor of 6. I said the order is not important for our selection, so we can basically start with star 2 after star 1 was selected, and the same for star 3 after star 2. So this kind of sub-range introduces basically this division by 6 and times n-1 times n-2. So if you would count the loop iterations here inside, it would be actually exactly n/3. So now we check if it's inside. Yes. If blue inside S1, S2, S3, perimeter result equals, we take the minimum of the previous thing we found and the current new parameter, parameter function from our 3 stars. Actually the parameter 3 function, because we need also the parameter of 4 points. Let's call it length, and explicitly add those 3 edges. Yes. Now we need to check if it's on one of the 3 edges, edges of the triangle, because then we need to do this construction and find the other potentially 4th point. So if connects through blue S1 count S2. So in this case, S1, S2 connected has an edge on which the blue star is. So in this case, you need to iterate S4, and S3 is the other corner, so S4 and S3 have to be another line where the blue star can be on. So S3 and all those points can be, all these S4s can be potentially the one we are looking for, because they're guaranteed to now have the red star in it. So we update the result again. we need to watch out for the order because S1, S2 is now no longer connected. So S1 is with S3 and S1 is with S4 connected. And S2 is with S1 and with S2 is with S3 and S4 connected again, like this. Yes. Now we have the other three cases. It might be that the red star is actually on the line S1, S3. So the other point is S2. Now S1 is connected with S2 and S4, not with S3, and S3 is connected with S2 and S4, like this. And the third case, if S2 and S3 are the edge where the blue star is on, and S1 is the other corner, S2 and S3 are not connected. So S2 is connected with S1 and S4, and S3 is connected with S1 and S4. So this should be the whole solution. We just have to implement this blue inside function for 3 points and the length function, which is very simple. Let's start with the length function. Start endpoint. I think there's a norm function even. I'm not sure if it returns. I need to check that. STD norm. Thought it was a lambda function really. And I'm not sure if the return value is always the norm value of a complex number is its squared magnitude defined as the addition of the square of both real and imaginary. This is square of ab, so we need to take the root. It's automatically. We will check this explicitly. Okay, it's called square root L. Okay. And now the blue inside function, which is the bool question. What is the easiest way to check this? I could look it up, but let me draw something for you. I think it's more helpful. So we have our 3 points, or stars, and we have some other point, which in this case, for example, is outside of the 3 points. If we take this point as origin, and we have 3 vectors basically. Maybe first of all we should check that these 3 points actually define a triangle and not are not on a line. I think the easiest way to do that is actually calculating the cross product between these two. So let us put all into an origin coordinate system. S2 times x times S3 times y minus 2 times y times S3 times x. If crossed 3 equals 0, that means it is actually they are on a line, and in that case the blue point can't be inside, so we turn false. Now we are in the case where we have a real triangle. That's already better. Now basically these two span vectors, they pop up a grid, like a strange grid, which you could draw. And if we compute the coordinates of this blue star relative to this grid, we could check if it's in this triangle very easily by checking that basically the coordinate is positive, so that it's in that direction from this line, it's in that direction from this line, and in that direction from this line we would check by seeing if the sum of the coordinates is smaller than 1. And the coordinates in this coordinate system is, I think, just dot product. Divided by the length of this one or the other axis. So scale x, scale 2 is maybe dot product of S2 plus yeah. So if we would divide this by the length of vector 2, then this would be a number between 0 and 1, hopefully, otherwise the point is outside. But I want to again avoid doing, like, computing the length of vector 2 would be using a square root, which would put us in floating point precision and not integer precision, which we think we need that. I should try to stay there. Let's just do it like this actually. So same we do for the other coordinate. Now I said we need to check both of them are positive, I think. Let me just think again. If this is our origin, this is our first vector. This is our second. the red point is here, for example, the blue star, then the scalar product of this one with this one would be actually negative, but it would be obviously inside the triangle. So somewhere here's my logic wrong, obviously. What I want to do is, of course, compose this vector in these two parts that are parallel to our base vectors, so something like this. In this representation, both vectors are basically positive with respect to the base span vectors. And I just have forgotten how to do that correctly. So if I have two vectors, this yellow vector which I'm about to draw, this one here, is, I would say, red dot product with, let's call this y. This is basically our x-axis. This is a scalar. And we know that to be equal to cosinus alpha times the length of red times the length of y. And the yellow vector, the projection y, is equal to cosinus alpha times the length of air times, now we need a direction, which is y divided by y absolute. And this cosinus alpha times r, we can see from this above formula, is r times y divided by y times y divided by y. Okay, so it's y squared is actually an integer, that's nice. It's a norm function. So this r times y is this thing I computed. But what I actually want is relative to this y vector, this value, which is actually cosinus alpha times r. This is just the thing the number I'm interested in. Which is sorry, I'm breaking down here. This is like, I think, the totally wrong approach. If I have my red vector and I have my x-axis and my arbitrary y-axis, I want to split my vector into these two components. So it would be something like this and this. Now we have, we'll just write in white. This R, Py, and Px. We have R equals to Py plus Px. And if I multiply this with x dot product, I have Py, and Py and x are not perpendicular. So this is not 0, but Px times x, they are actually parallel. So this is equivalent to x times x, which is and Py times x is equal to let's say Px and Py are equal to Ry times y. So this is the scalar we are actually looking for. And then we can say Py times x, we substitute this, is Ry and y times x, which is a fixed constant. And Px times x is actually Rx times x squared. We can compute Rx, we can compute Ry. We have Ry times y squared plus Rx times x y. Oh, and we need to invert to get those numbers. How is this so difficult? I'm really a bit surprised. So now I'm really, I will Google, sorry. This is, I'm so sorry if you got there quicker or have already the solution. I really forgot how to compute. Point inside triangle. There are no divisions, which is nice. You know what, I will just copy this. And so they say they just check on which side the point is. So if it's from left, from walking, when I'm walking from V1 to V2 and it's on my left, and I'm walking from V2 to V3 and it's on my left, and if I'm walking from V3 to V1 and it's on my left, then the point is inside. So these D1, D2, D3, which are signs, basically they all have to be either positive or they have to be all negative. So if it's always on my right, then it's also a triangle in which the point is. So this makes very much sense. Just have to fix this. This is blue inside. here's just blue. We can delete it from here. That should have been it. Sorry, that was like I should have done that from the beginning. Now let's copy these examples over. See what our algorithm does on this. In which line is this? 1147. Break it too much here. Oh yeah, sorry, and then probably here as well. Okay, we get a wrong result for the second test set. The first one is okay. Found that it's impossible. For the second test case, we get a value of 4. Okay. Let's check what the length computation does there. We have 1, 1 and 4. Oh, sorry. S and E are of course just the points. These need to be converted to stars. Yeah, sure. And there's a slight difference, but I guess that is okay, because we're rounding there. Let's maybe define another test case where there are actually 4 points. And the blue star is just in the middle. The optimal answer would be 2 times 4, so 8. Oh, it's 6. Okay, yeah, that's wrong probably. I'll fix this test case. Oh, sorry. Fix it the wrong way around. So what is wrong with case 3 in this case? These two we don't need anymore, they're fine. Let's check what the line connects to blue says. So 0 has the 3 point, 1 has 2, 2 has 1, 3 has 0, that's correct. Because I've just drawn a square basically, and here the opposite of 0, 0 is 2, 2. So this is position ID 0 and ID 3, and this is ID 1 and ID 2. And 1, 1 is the center point where I put the blue point, the blue star. So that is correct. Now, this sign computation is, it is really the cross product again. And we are really checking here that they are, I think the check here might miss if something is 0, yes. So they all have to be strictly positive or strictly negative. All negative. We have to connect that with an AND. All positive. Otherwise, I guess it took now the triangle where it takes 2, 2, and the product 2 square root of 2. 2 plus 2 plus 2 times square root of 2, which is 6.828, which is exactly what it computed. So we need to get rid of this case. So it needs to be all negative or all positive. Otherwise, it's not really inside. Oh yeah. Yes, that looks better. So the square works as well. Let's check if the solution is accepted. Fast enough it should be. It's n to the power of 3 speed. I mean, plus these 4 loops here inside this n to the power of 3, but I guess every line only appears at maximum twice here, and the number of lines is just n squared. So, but we have given a wrong answer for test set 1. That is really sad to hear. I'm asking myself where the mistake is, if it's with the impossible or if we didn't find the minimum. Did I rewrote something here wrong? If it's on S1, S2, then S4, S3 are opposite. So S1 with S3 and S4 and S2 with S3 and S4. If S1 and S3 are opposite, and S2 and S4 are opposite, we have 1, 2, 1, 4, and 3, 2, 3, 4. 2, 3 are opposite and 1, 4 are opposite, so we have 2, 1, 2, 4 and 3, 1, 3, 4. That looks all pretty much correct. We always take the minimum. I'm checking if the line inside is correct by putting here a 0.33. So 2, 2, 3, 3, 1, 1 are all on one diagonal, but these 2 points don't contain the blue point. Let's see if that is implemented correctly. It seems not, because, no, see, 0 says it goes through 3 and 4, which is the 2, 2. So if I connect this with this, or this with this, both times the 1, 1 is contained. But from 3 to 4, they both only connect to 0 through blue, and not to the other one. Okay, so that is correct. Seems correct. Can I find other examples which are non-optimal. So I think what I will do is download. This looks pretty much like the solution we had. Okay, so I just downloaded the test data in order to finish this video up, finish the debugging. I have found here test case 51, which the ground truth says it's impossible, but it seems my solution produces a 6. So we will have a look at test set 51. Ground truth says it's impossible. So I will put this into my local test. Oh, here. Now we just have to find the 51 test case. Oof. Which is actually not that easy. Can we find something more earlier? Problem is it shows a lot of diffs because the numbers are not correct to every digit. It looks like, but it looks like that the numbers are all basically correct. Just the was the only case I found that was not correct, the impossible thing. It really seems to be the only case. Okay, so I have to find that one. Should be in the middle, so maybe we can just look the number of lines. Then there are more 10 things. One, 2, 3, 4. So this should be 50 and this should be 51. Let's hope I got that right. Yes, I got it right. Our code still produces a 6 over there. Mysterious. What is going wrong here? These are all small, nice numbers, so I will draw this. The blue stars are at, let's say here's our origin. Oh, we have small numbers, so I can draw big. 1, 0, 2, 1. 4, 1, 2, 0, 3, 0, 1, 1, what, 4, 0, 0, 0, 0, 1, 3, 1. Okay. easy enough. 3, 1 is actually 1, 2, 3, 1 is the red star. Now I can see immediately that that is not possible. But why does our algorithm think that 6 is the optimal solution? 1, 2, 3, 4, 5, 6. It's probably trying to draw this triangle, this rectangle. How is that happening? But fair enough. Let's check if it's finding a triangle. I don't think so. Nope. One and this 2 are opposite. Here, let's make it the same here. Quite a lot of shapes are proposed. And I should number these actually over here. So 1, 0, this was our 0th point. 2, 1 was our first point. 4, 1. Second. 0. 3, 0. 1, 1. 4, 0. 0, 0. 0, 1. From 0 to 8, 9 points. Okay. Now it says, for example, 1, 2, 5, 2. What? It takes points double. 1, 2, and 5, 2. Oh, those are all on a line. So it finds 1, 2, 5 and then sees, for example, that 5 is opposite of 1, 2. Oh, sure. For the blue inside, we actually have the check. Oh, I actually deleted the check. But because it has to be strictly inside, if all on line, then we continue because we don't have to check the quadruples. And I think if they are not all online, then this is all fine. I hope so, at least. How did we check if they were all online? think we can take here again the sine functions. Oh, actually just one. And we got the correct value. The impossible value. So let's see if that is better. Yes. So we solved the problem. Phew. A few edge cases. Fair enough, I overlooked that one with the quadrilateral, four-sided shape, four-sided polygon, that's what I would call it. I can pronounce that. I think we did a good job in watching out for doing only integer-based calculations and only in the end doing this floating point summation of the length of the sides, otherwise avoiding it, so that we have an accurate information of the blue point's location relative to our proposed polygon. Yes. Solver line is a bit annoying. And this, of course, is very sad that I couldn't come up with it, and it's quite easy and nice implementation actually, nice symmetric between 1, 2 and 3 points. I'll try to remember that. And yeah, it's quite surprising actually that just the enumeration of all possible polygons is just fast enough, that you don't need, like, at the beginning I was a bit afraid that we need to do something like starting with a convex hull and basically cutting stuff off in a greedy wise way, and I quickly saw, like we saw with the triangulation, there are many possibilities, and some of them might be better and some of them worse, and when you do a greedy approach, it seemed to me that it was not clear how to cut. And if you would have needed to do this approach, because this cutting of course would be more in the runtime order of just n, because every time you cut just 1 point or so. Not sure there, but it seemed like that could have been possible, and I was looking for that solution, but because also it was in the beginning not clear if the shape might be more complex than triangles and four-sided polygons. But yeah, to establish this fact basically via some simple reasoning, minimal reasoning, also a big help, and then reducing this n/4 case to also this n/3 and just looking up some connections made this very fast and very possible. So, does it actually say how fast it was solved? Because I think, sadly it doesn't. Because I think it should be pretty fast. Actually, I can check it on this test set 3. Let's time it. Oh yeah, it takes a bit. Okay, I would have expected it to be much faster actually. Interesting. So yeah, I hope this helped you to prepare for your next competition or interview with one of the big companies, software companies. So, but really, if you do interviews, also good thing to participate in these upcoming events of Google. They will like to see that on the resume, and if you can talk about it. Yeah, so I hope you learned something, especially on how to approach the problem. I will upload this solution together with my sketches, which again got very are all over the place, I guess. I will upload it to my GitHub repo, links in the description. And yeah, please like the video, subscribe, ring the bell, and see you next time. Bye.